Hello everyone and welcome to this video. Today we're gonna cover an overview of computers and programming languages. And so this is an introduction to programming one course at university for the electrical engineering program, or the course is universal for even computer science students or industrial engineering students or any other specialty. And so this is a PowerPoint from the university. So as you can see, you can start. So the course learning outcomes is to describe the parts of computer architecture and the phases of developing a computer program, including flowcharts. And so we're gonna go through the computer systems, computer architecture and organization, computer software, programming languages, simple C++ programming and problem solving, and algorithms. And so a computer program basically is a set of instructions for a computer to follow. So that's a computer program. And so now let's go to a computer software. Computer software is a collection of programs used by a computer. So a software is a collection of those programs. So if we have a software is a set of sets of instructions. And so it's a set of programs, and so it includes editors, translators, and system managers. And so we have also the hardware now. There are three main classes of computers. They are PCs, which are personal computers. So they are relatively small, used by one person at a time. And now there is the workstation, which is a larger and more powerful than a PC. So, and you would regard that as used in maybe for servers and these more powerful or more demanding applications. And so we have also the mainframe, which is still larger and requires support staff and shared by multiple users. So these are the different workstations available to us. Now, if we open a new tab and try to take a look at this, we're gonna see here, if we go, so PCs, a PC is just these, this is a personal computer that you can use. This is an example of a personal computer. And now let's see the workstation. So workstation. So a workstation is a larger set of PCs. So it could be shared, it could be just, so it could be shared, most common at universities. As you can see, this is a workstation. And now if we say the mainframe, okay, so the mainframe is this is the one used for servers and, the more demanding applications such as testing and, programming, AI development. Now currently, all of these things that demand a large set of computers. This is a mainframe and it needs staff. It needs constant service and maintenance and looking after. And so as you can see, this is the mainframe workstation and PCs. And now we have computer organization. As you can see, this is the computer organization. This is the motherboard, as you can see down here. And here is the CPU, which is placed under the fan. This is the fan for the CPU. This whole thing is the fan, and then the thing placed under it is just basically the CPU. Here we can add graphics cards. Here this is the memory, which is for short RAM, and then we have the motherboard. We have also other components in this motherboard or PC. So this is the part basically needed for running a PC. Okay, there are also additional parts that are gonna be covered later during this course. And so we'll have computer architecture and organization. So there are five main components. So there is the input devices, output devices, the processor, main memory, and secondary memory. All of these are the main components of a computer. And so the main components, as you can see, the CPU is very important, and having a main memory is important also. So the main memory contains just the running programs, okay? Contains all of your data, all of your files, folders, programs, the Windows operating system. It contains all of these, and this is the main memory. And then there is the secondary memory, which is a permanent record of data, okay? Or maybe, okay, maybe I mixed those. So let's see which one. Okay, this main memory. This is secondary. Okay, so it's the opposite. So the secondary memory is the permanent record of data, which contains the folders, the windows, the programs, all of these. Now the main memory it contains the running programs. So any running program will be contained in the main memory. And so this is basically the RAM. As you can see, this is this part, this is the main memory, and the secondary memory is just containing all of the other data. Okay, your files, your folders, your programs, and so on. And now there is also input devices, which are, say, your keyboard, your mouse, your touch screen if you have a touch screen, etc. And the output devices are just, speakers, your screen, the LED, and a camera is an input device, and other stuff. So yeah, so that's basically the main components of a computer. And now computer memory. Now let's go through the computer memory. Okay. Now the main memory or RAM. Now this is where I just had a slight mistake. So the main memory is the one which is the running program is in. So it's the RAM. Okay, which is random access memory. So it's a long list of memory locations, each containing zeros and ones. So it's zeros and ones. So it's still the same as the secondary memory, but the difference is that it can change during program execution. So it changes constantly, and so it works on a binary digit or bit, which can be 0 or 1. And each memory location has 8 bits, which is a byte. So a byte is 8 bits, and then the address is the number that identifies a memory location. And so yeah, so if you want to access a specific memory location, we're gonna address it and use the address. Okay, and so yeah, so basically it uses the byte, it's binary digit or bit, uses bits, and yeah, so these are all definitions. Okay, so as you can see, these are 8 bits, 8 bits, 8 bits, so these are all divided now here. Okay, so say this 8 bits, maybe, or this is more than 8 bits. No, this is more than 8 bits, because RAMs basically can go up to 8 to 16, even 36, 64 GBs. So GB is way more. So this is not only a single bit byte, it's more. It could be, if this is 8 GB, could be each one of this is 1 GB, 1 gigabyte. Okay, gigabyte. So one of these could be 1 gigabyte. So it's not a small number. And so for larger data items, so yeah, so some data are too large for a single byte, and so yeah, so most integers and real numbers are too large. So these are large integers and real numbers, and so the address refers to the first part, and then next few consecutive bytes can store the additional bits for larger data. And so the address will refer to the first byte, and then the following bytes will be stored and will contain the additional bits for larger data. And so as you can see, so 2 byte location with address 4. Now this is address 4. The address of this is 4. So byte 4 is 2-byte location with address 4. Now this is 3-byte location with address 1. So you address the first byte and then you specify how many bytes are you using, how many byte locations are you using. And so is it data or code? So A may look like something like this, okay, in the main memory. Now 65 may look like this, and an instruction may look like this. And all of these will look differently, you know, in the main memory. And so they all have the same, you know, the same code. Now, how does the computer know the meaning of 0, 1, 0, 0, 0, 0, 0, 1? Now, this depends on the current instruction. So programmers rarely need to be concerned with this problem, because they rely on what are known as compilers and assemblers. So these make our lives easier as programmers, and they basically change written code which is understandable by us humans into code that's understandable by machine, which is zeros and one. So this is the job of compilers and assemblers. They convert assembly language up to machine language, to machine language. So they can understand it, and also we can understand this. And so now let's go over secondary memory, which stores. So the main memory stores instructions and data while a program is running. So while a program is running, it stores that data. However, secondary memory stores instruction and data between sessions. So a file stores data or instructions in secondary memory, and one example of it is just hard disk. So this is where all of your programs that are not running but stored, and your files, your windows, all of these are stored in the secondary memory, which is the hard disk. And now let's go to the processor. Now typically called the CPU, is the central processing unit. The processor, CPU, stands for central processing unit, which follows program instructions. And typical capabilities of a CPU include is adding, subtracting, multiplying, dividing. So it adds, subtract, multiply, divide. And also it can move data from location to location. So these are the main capabilities of a CPU. And now that doesn't mean that it cannot do what it does. It does very astonishing things with our computers, as we know. And And so we have the computer input output. So computer input consists of a program, as you can see, and some data. So a simple view of running a program. There's a program and data, and there's computer, and all of these, and there is the output. So we need program, a data, computer, and this will give us an output. Now for computer software, the operating system allows us to communicate with the computer, which is a program. So it allocates the computer resources and responds to user requests to run other programs. So this makes it easier to us to use and communicate with our computers. And also some common operating systems include Unix, Windows, Linux, Mac OS, Macintosh, DOS, VMC, VMS, and etc. These are all operating systems. And so now we're gonna go through the programming languages. So there are a couple of different programming languages. And these include machine language, assembly language, and high-level language. We're gonna go through it. Now, machine language is a set of primitive instructions built into every computer, which is basically ones and zeros. So this is like built in every computer. And the instructions are in the form of binary code. So you have to enter binary codes for various instructions, which could be hard for a person to try to do, since you need to memorize all of the sets of instructions. And so that's why there are different types of programming languages that help us communicate with the computer. And so program with native machine languages is a tedious process, and yeah, so it's highly difficult to read and modify. And so for instance, to add two numbers, you might write an instruction in binary like this. So 1101 means add. Now 42 in binary is just 101010, and 26 is 011010, and now this basically will add 42 to 26 in the processor, and this is very tedious. And so every computer system is used to punch the zeros and ones on special cardboard paper, as you can see. And yeah, so these can be modified easily. So, and imagine making a single mistake and you have to do it all again. Impractical. And yeah, so computer designers will agree what operation the first 4 bits indicate. And so as you can see, programming languages. Now we go to assembly languages. Now assembly languages were developed to make programming a bit easier. Now instead of writing programs in zeros and ones, we write the program in terms of the desired operation, which is add, sub, move. So we want to add, number, subtract, and also move some data. So the numerical numbers, memory locations, etc. And so since the computer cannot understand assembly language, we will need something called an assembler, which is used to convert assembly language that we use into machine language. And so as you can see, this is assembly language. This is a bit more easier to read. So as you can see, move R1 and then move R0, R1, and then add R0, R0, R1. So it'll add them all, and then you're gonna move. So this is basically assembly language, and then an assembler converts this assembly language into a machine code. And so to add two numbers and print them, we'll write a code like this. So add 2, 3, and then the result, and this will give us a result of 5. And now going to high-level languages. So these are so there are first dozens of computer processor types: Intel, AMD, so found in PCs, laptop servers, and there are also ARM, which is found mostly in tablets, phones, and laptops. And there's also MIPS, RISC-V, and etc. These are all computer processor types, and so each one of them has a different design, different machine code, and different assembly language. And so imagine learning different assembly languages to develop a program that runs on all of these different computers. That's very practical. And so what was the solution? The solution was developing a high-level language written once and translating it to different assembly languages as needed. So one program runs on many machines. And now the most revolutionizing thing about high-level languages is that they are English-like and easy to learn and program. So for example, the following is a high-level language statement that computes the area of the circle with the radius 5, and so the area is just 5 squared times 5, and that's basically the area, and it's basically like math. So you multiply 5 times 5 times pi, which is 3.14, which gives us the area. And now there are many high-level languages, and they are old and they are new. So the old ones include COBOL, so Common Business Oriented Language, Formula Translation, BASIC, which is Beginner All-Purpose Symbolic Instructional Code, Pascal, Ada, Delphi, and all of these. And now there is also now the popular high-level languages, which is C, which is used in hardware programming, which is similar to C++. Now there is Visual Basic, which is basic like visual language developed by Microsoft. There is now C++, which is an object-oriented language based on C, and Java, which is an object-oriented language. Also, there is object-oriented languages, which is also similar to C++. C#, a Java-like developed by Microsoft. MATLAB for engineering and scientific applications. Python, widely in data analysis and artificial intelligence, widely used. JavaScript, front-end, back-end, and mobile development, and also Go, Ruby, Swift, Objective-C, Rust, Scala, Perl, and all of these are types of languages, as you can see. So we can convert from high level to machine code by compiling, okay, or interpretation. So there is compiling and there is interpretation. So Python and MATLAB have interpreters that translate and execute a program line by line, okay, as long as they are correct as seen in the figure, as you can see. So an interpreter executes a program line by line. Now C++ needs a compiler that translates the entire source program into a machine language file. So a compiler translates the entire source code. Now this is the difference. An interpreter does it line by line, but a compiler does it, for the whole file. And so all the program must be in machine code before execution. And so you need to think of it as giving an English document to a translator, and they hand you the Arabic version. And so yeah, so it's like translating the whole document. However, for an interpreter, you can think of it as being in a conference room and someone is translating the speech from English to Arabic as the person speaks. So it's live translation. And that's basically an interpreter, as you can see, translated from high level and gives us an output. A compiler translates to machine code and then gives it to an executor to give us an output. As you can see, so translates to machine code. Interpreter, okay. And so, as you can see, compilers translate high-level language to machine language directly. So it goes from high-level directly to machine language. So high level, it goes to machine language. So I'm writing this as a note, and you can write some notes with me also. So let's say we have a C++ program. Now we have a compiler, we have a computer, we have then it goes to machine language program, and goes then to the computer. And so here data for C++ program is provided, and this is the C++ program. Okay, so we can regard this as the data, and then gives us the output of C++ program. So there is the source code, the original program, which is in a high-level language, and there is the object code, which is the translated version in machine language. Source code and object code. These are the different types of code. So source code and object code, as you can see. Now let's go to linkers, and these are basically so some programs we use are already compiled, so their object code is available for us to use. For example, input and output routines. Okay, and so a linker combines the object code for the program we write and the object code for the pre-compiled routines into the machine language program the CPU can run. So it converts the object code for the program and the object code for the precompiled routines into the machine language, and this is the job of the linker. So the linker is basically a compiler, okay, with the addition of converting the object code also for converting precompiled routines also, and the addition of that into machine language. So it compiles source code plus precompiled routines into machine language, and that's the role of a linker. And now let's see. So preparing a C++ program for running. Now C++, a compiler basically convert to object code for C++ program. Okay. And the linker just converts the object code for other routines. And then we have complete machine language code ready to run. So it adds the object code for other routines. Now let's see a simple C++ program. So as you can see, we have include IO stream using namespace std. So we're gonna start int main. Okay, so this is basically an object, as you can see. Okay, so here we display welcome to C++. And then now to do that, we're gonna go to count, and then we're gonna have two arrows like this, and then welcome to C++, close it with a semicolon, and then return 0 to close this function, is it, or object? So it's mostly the main function. I think it's the main function. And as you can see, you can do that maybe by going to C++ online compiler and trying to do that. Okay, so this is basically already written to us. So welcome to C++, and we run this. So this is basically the compiler. When we write hashtag include IOStream, it is a C++ compiler to run a C++ program. And here basically that's how we do it. Here we need std, and we can add return 0. It's already there. There are also some special characters in C++. So the pound sign is used to denote preprocessor directives, so like commands. If we want to add comments, we can use the pound. Okay, the pound sign. And now there is also the opening and closing angle brackets. Okay, these encloses a library name when used with hashtag include. Or actually, the hashtag sign can be used with include here, as you can see. Sorry, so it's using with include to denote a preprocessor directive. So this is to include a directive like this. And now the brackets are used, encloses a library name. Now, yeah, so this is used to indicate to include a library, and this is used to include a library name. And so now we have opening and closing parentheses. These are used with functions such as main. So this is a function. Okay, int main is a function. Okay. And now we have curly braces, opening and closing braces. So these denote a block to include statements. So for example, here we have this block, which is our function. So these enclose a block. Double slashes precedes a comment line. Now this is the comment. If we want to add a comment, we can just double slashes. Hello, this is my program basically. And so we have also the stream insertion operator, so it outputs to the console, so this is used to print something out to the console. And now we have also the quotation mark, which is opening and closing quotation marks, which wrap a string, so which is a sequence of characters. So here for our example, this is used to print. If we want to print something else, we write std count cout and then like this, and hello world like this, and we close with a semicolon. And semicolon marks the end of the statement, which is important. We have also the program layout, which include directives, which is one of them is include isostream, which tells the compiler where to find information about the items used in the program. So this is the compiler. It's a library containing definitions of sin and cout. So this is what is used to print out. So yeah, so that's why we import it. We need to import it to print out some, if we want to print out to the console. And so using namespace std tells the compiler to use names in isostream in the standard way. So std means just use the names in iostream in a standard way. So that's the difference basically. Now if you remove this, I'm not sure if it's gonna run. No, it gives us an error. So we need to use in a standard way. Maybe it's due to the online compiler. And so to begin the main function of the program, we're gonna write int main, and then we're gonna have this brace, curly brace, and then to end the main function, we're gonna go return 0 and then close it. And the main function ends with a return statement. Main function ends with a return. So you can return just 0. So there is also this thing and debugging. So a bug is basically a mistake in a program, and debugging is eliminating mistakes in a program. And now program errors, there are a couple of errors, which include, first of all, we have syntax errors, which is a violation of the grammar rule of the language. Okay, so it's discovered by the compiler, since it's easy to identify by the compiler, and error messages may not always show up. Correct location of error. Just there is, yeah, sometimes the error messages do not show the correct location of the error, but it certainly detects errors, since they are easy to detect by the computer. Now there is runtime errors, which are conditions detected by the compiler at runtime. So for example, we have the division by 0 error. When you divide by 0 during runtime, this will produce an error for you. And now there is the logic error, which are errors in the program's algorithm. So for example, adding and subtracting. So maybe if you add 1 plus 1 and your program produces 3, now this is a logic error, which is an error in the program's algorithm, which is the most difficult to diagnose. Okay, and the computer does not recognize this as an error. Now we have programming and problem solving. Now we can go through algorithms, and so an algorithm is a sequence of precise instructions that leads to a solution. Okay, that's an algorithm, and it determines how many. So it's a sequence of precise instructions. It's a sequence of instructions that leads to a solution. That's an algorithm. And there are many types of algorithms. There are more complicated ones, and there are very basic ones. And so there is also then a program, which is an algorithm expressed in language that computer can understand. A program is an algorithm expressed in a language that the computer can understand, so it's in machine language. And so let's say we have an algorithm that determines how many times a name occurs in the list of names. So first you're gonna get the list of names, then you're gonna get the name being checked, you're gonna know which name are you checking for, and then set the counter to 0. Okay, and have a variable set to 0, and then do the following for each name on the list. Compare the name on the list to the name being checked. So for each name, you're gonna compare it to the name being checked. If the names are the same, add 1 to the counter, add 1 to this variable, and repeat this loop through this to get the final number and the number of, times a name occur in the list. And then you can announce that number. That the answer is the number indicated by the counter, which is used by printing. So we can print this std count and print here add the variable to print. And we have now the program design. So yeah. So I think I'm gonna stop here with the algorithm. Okay, and that's all. I hope this video was helpful to you. We'll see you later.